Welcome to the High Voltage AI podcast. This is the deep dive, and it's where we unpack a stack of our sources, extract the most important nuggets of knowledge, and offer you a shortcut to being truly well-informed. We dig into the surprising facts, always with, just enough humor to keep you hooked, and every deep dive is custom-tailored for you, our listener.
That's right, and for those of you following along, you know this deep dive is part of a special week-long series featured in the High Voltage AI newsletter on Substack. We've been exploring the really transformative world of grid forming technology all week.
What an incredible week it's been, seriously. We kick things off Monday, digging deep into the fundamental differences between grid forming and grid following. Really crucial stuff for the future.
Absolutely foundational.
Then Tuesday, we pulled back the curtain on how synthetic inertia actually works. Giving the grid that stability from renewable.
The magic behind the curtain, yeah.
Wednesday, we tackled the real nitty-gritty. System integration challenges, protection, coordination, navigating those complex grid codes.
Always a challenge, that integration piece.
And just yesterday, Thursday, we brought it all to life. Real-world applications, looking at Australia's mandate and the big storage deployments in Texas.
Seeing it in action really makes a difference. And today, Friday, we're bringing it all to, I think, an exciting culmination. Our focus is career opportunities, power electronics expertise in the grid forming era.
Right. It's about how this huge technological shift is reshaping engineering careers and, importantly, what it means for your professional future.
What's so striking, and our source material really brought this home, is that this isn't just theory anymore. The opportunity is immense.
Yeah, that Tesla example was quite eye-opening. They posted a job for a grid-forming inverter control engineer.
Offering, $180,000 to $250,000.
Exactly, and they got over 400 applications in just 48 hours.
Wow. That says a lot.
It really does. And that specific role, combining power electronics expertise with grid integration knowledge, it perfectly captures these new hybrid specializations popping up.
Highly sought after, clearly.
So, our mission for this deep dive is pretty clear. We're going to unpack exactly how this tech transformation is reshaping careers, what specific skills are commanding those premium salaries.
And maybe most importantly, how you can best position yourself for success in this grid forming era.
Okay, let's unpack this.
So historically, if you think about engineering disciplines, these two were really quite separate worlds.
Right.
You had power electronics engineers, almost like microsurgeons, right? Focused on semiconductors, switching circuits, control systems for inverters, converters, the device level.
Very intricate stuff. And then on the other side, power systems engineers, more like the grid architects.
Exactly. Their focus was the big picture generation, transmission, distribution of bulk power across the network.
And the key thing, as our sources highlighted, wasn't just a division of labor. It was almost like a philosophical divide sometimes. Siloed design.
Definitely. Minimal interaction in most traditional utility applications. They almost spoke different languages, you could say.
But now, that separation is just crumbling. Fast.
It really is.
Yeah.
With grid-forming tech, modern applications absolutely demand deep expertise in both domains, no question.
So suddenly, these power electronics control systems are doing things that only big spinning generators used to do for grid stability.
Precisely. Power electronic devices are providing services, system services, traditionally from large generators. And it's not just function.
It's also about meeting those really stringent utility interconnection requirements, right? The grid codes.
Grid codes, absolutely. Think IE 1547, UL 1741, all those utility specifics, these devices have to meet them.
And on top of that, they're active in the markets now, providing ancillary services, capacity.
Yes, actively participate in frequency regulation, voltage support, you name it. This convergence, it's created these new hybrid roles.
Okay, here's where it gets really interesting.
Indeed. And if we look closer at these new hybrid specializations, the first one that jumps out, maybe the most pivotal, is a grid-forming control engineer. These are the folks designing and implementing the virtual synchronous machine algorithms, essentially programming inverters to act like stable generators.
Giving the grid that synthetic inertia we talked about Tuesday.
Exactly that. Their technical skills need to cover digital control theory, core power electronics, synchronous machine modeling, quite a mix.
And system knowledge, too. grid codes protection.
Grid codes, protection coordination, making sure everything plays nice in market operations. Plus, software skills are key.
Like MATLAB Simulink, CC++.
MATLAB Simulink, definitely. CC++ for real-time control, Python for analysis, real-time programming in general.
And the salary range for these roles?
The sources suggest around $140,000 to $220,000. Reflects the demand.
Wow. Okay, beyond the core control design, what else? You mentioned another key role.
Yes, the power electronics integration specialist. This is critical. Their job is integrating these inverter-based resources, the big batteries, solar farms, with the existing grid.
Making it all work together seamlessly.
Exactly. They need strong skills in power, electronics design, protection systems, grid modeling, and often, crucially, project experience.
Real-world experience on large-scale projects.
Yes, renewables, storage projects, and they need regulatory knowledge, too. IE standards, grid codes, those tricky interconnection processes.
Right, navigating all that. Salary range for senior specialists here.
Typically around $130,000 to $200,000 for senior roles.
Still very strong. And you mentioned a third level.
At the top, you have the grid-forming system architects. These are senior engineers designing the comprehensive solutions, end-to-end.
The big picture thinkers.
Right. They provide technical leadership, guide multidisciplinary teams. They need business acumen, too, market analysis, project economics, tech roadmaps.
Understanding the financial side is key for architects.
Absolutely. And strategic planning, long-term tech development, and deployment. For principal or director levels, you're looking at salaries from $180,000 up to $280,000.
Okay, those figures really underscore the value. It could definitely make a traditional power systems engineer think hard about adding some new skills.
It's a significant shift in valuation, absolutely.
So let's peel back the layers then. What are the actual competencies, the specific skills that are commanding these premiums? What's in highest demand?
Okay, core technical competencies. It really starts with a deep dive into power electronics fundamentals.
What does that entail specifically?
Well, you need to know the components inside out. Semiconductor devices, IGBTs, silicon carbide, gallium nitride. These are the heart of it all, the switches controlling huge power flows.
Understanding their characteristics is key, right? Affects efficiency, size.
Crucial. Then switching circuits, inverter topologies, modulation techniques like pulse width modulation, filtering for clean power. Control systems are vital digital control, protection, fault handling, and thermal management. Can't forget that.
Keeping things cool when handling all that power.
Exactly. Heat dissipation, cooling systems, reliability analysis. Very important.
Okay, so fundamentals first. What builds on that?
Next up, absolutely essential, grid integration knowledge. This means a solid grasp of traditional power systems.
Load flow, fault analysis.
Load flow, fault analysis, stability studies, protection coordination, all the classics. But then you need fluency in specific grid codes, IEE 1547, UL 1741, plus utility-specific requirements.
The rules of the road for connecting.
Precisely. And understanding market operations, ancillary services, capacity markets, economic dispatch, how these resources actually earn money beyond just energy.
Right, the value proposition.
And finally, communication protocols. Things like IEC 62850, IE 2030.5, DNP3, Modbus. They're the languages the grid equipment uses to talk.
Got it. Power electronics, grid integration. What else?
Tying it all together is advanced control theory, going beyond the basics.
So not just PID control.
Well, classical control like PID and state space is foundational, sure. But also modern techniques model predictive control, adaptive control, robust control, designing systems that handle uncertainty.
Which is huge in grid applications with renewables.
Exactly. Nonlinear systems knowledge helps too. Lyapunov stability, sliding mode control. And increasingly, machine learning approaches are valuable.
Neural networks, reinforcement learning. For smarter grid control.
Yes, for predictive control, optimization, things like that. It's the next frontier.
Okay, that's a heavy dose of theory and fundamentals. What about the practical tools? Software and simulation must be huge.
Absolutely crucial. For design and analysis, MATLAB Simulink is almost ubiquitous for modeling power systems and control systems. Great for prototyping.
And for more detailed circuit simulation.
Tools like PLECS or PSEM are common for power electronic circuits. Let you test designs virtually.
What about grid-wide analysis?
There you're looking at tools like PowerWorld or PSSE for power system analysis and planning. And for really fast events, electromagnetic transients, you'd use PSCAD or EMTP.
A whole toolkit needed there. And programming languages.
Oh, definitely. Strong programming skills are non-negotiable. CC++ is critical for real-time embedded control. It's what runs in the inverter.
Makes sense. What else? Python.
Python's huge now. Data analysis, machine learning, automation scripts. MATLAB is still very widely used for algorithm development and prototyping. And LabVIEW is important for hardware-in-the-loop testing.
Simulating real-world conditions in the lab.
Exactly.
Yeah.
And finally, you need to understand the hardware platforms themselves.
Like the actual chips.
Yeah.
DSPs, FPGAs.
Right. Familiarity with DSP FPGA platforms, think Texas Instruments, TMS-320, Xilinx, Zinc. Also, real-time simulation systems like National Instruments, DSpace, OpalRT are key for testing.
And the power electronics hardware itself.
Of course. Inverter design, gate driver circuits, the nuts and bolts, and communication hardware, Ethernet, CAN bus, fiber optic, wireless, how everything connects.
Okay, that is a demanding skill set. So with all that in mind, where is the demand actually highest, geographically speaking? And what about those salaries again?
Right. Let's talk hotspots and compensation. Geographically, some places are definitely hotter than others.
California comes to mind first, I imagine. TSO region.
Absolutely. California is a leader in grid-forming deployment. Our sources say average salaries there are maybe 25 to 35% above the national average for these roles.
Wow. And who's hiring there? Tesla, Google.
Key companies include Tesla, Google, the big utilities like PG&E and SE, KSO itself, plus a lot of tech startups.
What's driving it there? Renewables targets, resilience.
All of the above. Aggressive renewable goals, wildfire resilience needs, storage mandates, creating huge opportunities in utility-scale storage, distributed energy, microgrids.
Okay, California's hot. What about Texas? ERCOT. Heard a lot about storage there.
Texas is another major hotspot. Rapid storage deployment is creating very high demand. Salaries are strong too, maybe 15 to 25% above national average.
Who are the key players in Texas?
Companies like Fluence, Tesla again, Vistra, NRG, ERCOT itself, and lots of development companies.
And the drivers are more market-based.
Largely, yes. Market-driven storage growth, massive renewable integration, and grid resilience are key. Lots of opportunities in big transmission-connected storage and virtual power plants.
Makes sense. What about the Northeast? ISO in New England, New York ISO. Offshore wind is big there.
Exactly. Offshore wind and electrification policies are driving demand in the Northeast. Salaries are also strong, maybe 20 to 30% above average.
Companies like National Grid, Eversource.
National Grid, Eversource, Con Ed, and the big offshore wind developers like Ørsted and Equinor. Growth is fueled by that offshore wind build-out, electrification policies, grid modernization.
So opportunities in wind integration, urban microgrids.
Urban microgrids, resilience projects, absolutely.
And this isn't just a North American thing, right? What about international markets?
No, definitely global.
Yeah.
Australia is a standout leader in grid-forming deployment, partly due to their grid needs. Europe has strong demand, especially for virtual power plant expertise and sector coupling.
Linking electricity with heat and transport.
Exactly. And
Yeah.
Asia, massive infrastructure investment means huge opportunities, especially in places like Japan, South Korea, Singapore as they modernize.
Okay, so the demand is widespread. Now let's break down the salary progression again. How does experience level impact that premium for grid forming skills?
Right. The premium is pretty consistent. For entry level 0 to 3 years, a traditional grid following background might get you $80,000 to $110,000.
But with grid forming skills,
You're looking at a 15 to 20% premium. So maybe $95,000 to $130,000 right out of the gate.
that's significant. What about mid-career, say 3 to 8 years?
Traditional power electronics might be $110,000 to $150,000. Add grid forming specialization, and you see a 20 to 25% premium, pushing the range to $130,000 to $180,000.
It really pays to bridge that gap.
It does. Then senior level, 8 to 15 years. Principal engineers might typically see $160,000 to $220,000.
And the grid forming experts in that bracket.
They're earning $180,000 to $250,000. Again, that 15 to 25% premium holds.
Serious recognition for that specialized knowledge. And at the top, leadership.
Leadership level, 15 plus years. Engineering directors, you're looking at $220,000 to $320,000. CTOs, maybe $300,000 to $500,000, depending on the company. The top roles really command executive compensation.
So given these numbers, does the type of company you work for also make a difference beyond just salary?
Oh, absolutely. The industry sector matters quite a bit. Utility companies, for instance.
Stable, good benefits.
Generally, yes. Industry standard base, pay for the region, excellent benefits, often pensions, job security, good work-life balance usually, a solid, stable path.
Okay. What about tech companies? Startups or big tech getting into energy?
That's where you often see a significant premium, maybe 20 to 40% above utility salaries, plus Equity compensation, stock options, potentially rapid advancement. Very innovative, fast-paced.
Higher risk, potentially higher reward. What about consulting?
Consulting engineering firms usually offer a 15 to 30% premium over utilities, often with project bonuses.
But more travel, maybe.
Often, yes. Significant travel can be part of it. But you get exposure to a huge variety of projects, clients, technologies. Great for learning quickly.
And finally, the equipment manufacturers, the ones building the inverters.
Equipment manufacturers offer competitive pay, often similar to tech companies. They can also provide international opportunities and really deep technical involvement in R&D. You're right there where the tech is being built.
Okay, lots of different paths. So the big question for many listeners, especially engineers maybe in traditional roles now, how do you position yourself? How do you make that transition?
Great question. Let's break it down. For traditional power systems engineers,
What's the priority for them?
skill development focus should be on power electronics fundamentals, learning inverter control, understanding of devices, also control systems digital, real-time, and programming CC plus Python, MATLAB are key.
And understanding the grid-forming concepts themselves.
Absolutely. Virtual synchronous machine concepts, how it all works. For a transition strategy, volunteer for internal renewable integration projects if you can.
Get hands-on.
Get hands-on. Attend conferences, i.e. Power and Energy Society, power electronics workshops. Look into university or vendor certifications. Network, i.e. Power Electronics Society, grid modernization committees.
What's a realistic timeline for that kind of transition?
Sources suggest maybe 12 to 24 months for basic competency, but 3 to 5 years to develop real, deep expertise. It's a commitment.
Okay. Now, flip side. What about power electronics engineers wanting to move more into grid integration?
For them, the priority is gaining strong power systems knowledge. Grid operations, protection schemes, system planning.
Learning the utility side of things.
Exactly. Learning grid codes and standards, i.e. FE 1547, utility requirements. Understanding electricity market operations, how ancillary services work. And utility communication protocols, cybersecurity.
How can they make that transition?
Collaborate with utility engineers on projects. Attend utility conferences to understand their perspective. Maybe take academic courses or even pursue graduate education in power systems. Network with utility folks, system operators.
And the timeline for them?
Probably looking at 18 to 30 months to get really competent in the grid integration application side.
Okay. What about recent engineering graduates? What's the ideal path for them starting out?
The optimal background would be an electrical engineering program, strong in both power systems and electronics. Coursework in control theory, good programming skills, and ideally internships.
Internships in utilities, renewables, power electronics.
Exactly. For an entry strategy, look for rotational programs at big companies for broad exposure. Consider grad school MS or PhD focusing on grid integration or power electronics. Startups offer great hands-on learning. Or vendor training programs.
How can they accelerate their development?
Find mentors who bridge both worlds that's invaluable. Work on cross-functional projects, be active in conferences, and commit to continuous learning. This field changes fast.
That continuous learning piece seems critical. Are there specific resources people should look into? Educational programs, organizations?
Definitely. For educational programs, look at university certificates. Georgia Tech has a good power electronics certificate with a grid integration focus. UC Berkeley, Virginia Tech, University of Wisconsin also have strong programs.
What about industry-specific training?
i.e. Power and Energy Society University has courses on grid modernization. CIE offers international training. EPRI has utility-focused training. And vendor programs give you deep dives on specific equipment.
And online learning. Coursera, EDX.
Great options. CourseRate X for university courses. LinkedIn Learning for professional skills. YouTube and webinars for free content lots out there. And always read technical papers, i.e. Explore is essential.
Professional organizations are key too, right? For networking and staying current.
Absolutely vital. i.e. Power and Energy Society technical committees, conferences, publications, local chapters must join for power systems, folks.
And the Power Electronics Society.
i.e. Power Electronics Society is increasingly focused on utility applications. They host the big ECCE conference, often with grid-forming sessions. Good career resources, too.
Any others worth mentioning?
Briefly, yeah. Energy Storage Association, Solar and Power International, Distributech for Distributed Energy, Clean Energy Group. All relevant depending on your focus.
Okay, so looking ahead now, what's the future career outlook? Is this trend going to continue accelerating?
All signs point to yes. The outlook isn't just bright, it's pretty revolutionary for engineers in this space.
What specific tech trends are creating these future opportunities?
Well, artificial intelligence integration is huge. Predictive control for grid forming algorithms, machine learning for advanced protection, AI for market optimization, predictive maintenance.
AI is touching everything.
It really is. Then advanced semiconductors, those wide band gap devices. Silicon carbide, gallium nitride enable better inverters, more efficient, smaller, tougher. Drives new integration tech, reliability engineering, thermal management.
Little chips making a big difference.
Huge difference. And communication and cybersecurity. 5G for low latency grid control, blockchain potentially for energy trading. Robust cybersecurity is non-negotiable for critical infrastructure. Edge computing for distributed intelligence.
Bringing the smarts closer to the grid edge.
Exactly.
And if we connect this to market growth, the numbers are big.
Staggering, really. The current global market for grid-forming inverters, maybe $5 billion annually now, projected to hit $25 billion to $40 billion annually by 2030.
That's a massive jump. Compound annual growth rate of...
Between 35 and 50%. It's explosive growth.
What does that mean in terms of actual jobs?
It translates to potentially over 100,000 new engineering positions globally, growth everywhere, but especially in those regions leading on renewables.
And specific deployment numbers, storage, renewables.
Projections suggest over 500 gigawatts of grid-forming storage by 2030. That's enormous. Most new renewable projects likely having grid-forming capabilities, more adoption at microgrids, industrial sites, and vehicle-to-grid applications expanding.
Your EV helping power the grid someday.
It's coming. So the bottom line for career planning.
It sounds like this convergence of power electronics and power systems is one of the biggest opportunities in energy for decades.
It really is. Engineers who develop expertise right at that intersection. They're positioned for exceptional growth, premium compensation, and becoming the technical leaders defining our future grids.
So let's recap those key career strategies again. 6 points.
Right. 1. Skill convergence. Get expertise in both power electronics and power systems. 2. Continuous learning. Stay current. The tech moves fast.
3. Market timing. Now the next 5-10 years is the time to establish yourself. 4. Geographic flexibility. Consider those high-growth hotspots.
5. Network development. Build relationships across both communities. And 6. Project experience. Get hands-on with real grid-forming projects.
So engineers mastering this won't just advance their career.
They'll play essential roles in the clean energy transition. They'll define how future power systems operate for generations. Which really leads to a final thought for you, the listener.
Okay.
Given this rapid evolution we've discussed, what new skill or area of knowledge are you most excited to develop to contribute to this grid transformation? Something to ponder.
A great question to end on. And that wraps up our week-long deep dive series on grid-forming technology. It's been quite a journey, from fundamentals all the way to career opportunities today.
It's been fascinating to explore. We're excited for next week. We'll be diving into small modular reactor engineering opportunities combining traditional nuclear expertise with modern grid integration technology.
Sounds intriguing. If you'd like to leave feedback or have any questions, feel free to reach out to our producer, Julius Guay, on LinkedIn. Remember, that's Guay, pronounced Guay.